Welcome back, guys. This is a question I got from one of the subscribers asking for some help or guidance in how to draw the shear force and bending moment diagram for the beam shown in the figure. So we have this beam. It's a little bit tricky. It has a hinge on B, and it's suspended by a cable between point E and C, and the loadings is shown in the figure. So my first step is to, and it's an advice for everybody, simplify your drawing as much as you can. We do this by drawing what is known as the free body diagram. This is the free body diagram. It shows the reactions Bx and By, and by just intuition we are expecting that the force or the cable has a tension force F, so it's going to be pointing in that direction. But if I want to solve for the reactions as a first step, I need to have all the forces to be either on the x or the y-axis. So I need to do something with this F force. Now this F can be resolved into two components, Fy and Fx. And I need to concentrate the distributed load, the 7 kilonewton per meter, and I concentrated it at a distance 10 meter from the right or the left, which is basically the center of the distribution of the load. Now I'm ready to go ahead and apply the three equilibrium equations we know, which are the summation of the forces in the x, the summation of the forces in the y, and the summation of the moments about a point, and set all of those equal to 0. So if we do the summation of the forces in the x, we get Fx minus Bx equals to 0, or simply Fx equals Bx. Again, this equation, for now, it's a little bit vague. We have no numbers out of it. So let's jump into the second equation, summation of the forces in the y direction. What do we have? We have By Fy equals 250 plus 50 plus 140. Okay? Now, again, I have By and Fy, two unknowns again. Let's do the third equation and see if we can get something out of it. The third equation, basically, it's summing the moments about a point. I chose the point B here to be the point I want to rotate about. So Bx, By, and Fx, all of these three unknowns do not play a role in the equation because all of them pass through the rotation or the point of rotation. If I do this, I get 250 times 20 plus 50 times 16 minus Fy times 16 plus 140 times 10, and set that equal to 0. From that equation I can solve for Fy, and I did. It turns out to be 450 kilonewton. Now I can substitute this number back into this equation right here and solve for By, and turns out that By is minus 10. So again, the minus sign here means that my assumption of By being upward is wrong, so it's going to be pointing downwards. Okay, now we need Fx and Bx. Fx and Bx can only be solved if we know F. How's that? F is inclined, okay, along the L dimension of this triangle. I need to calculate the value of L. L is 10 squared plus 16 squared under the square root, so it's 2 multiplied by the square root of 89. Again, I have this F. I want to resolve it into Fx and Fy. If I know theta, which is between, for example, Fx and F, Fx is going to be F cosine theta, and Fy is going to be F sine theta. But let's look at Fx, for example. Fx equals F cosine theta. But what is cosine theta? Basically, cosine theta is nothing but 16 over L. So it's Fx going to be F multiplied by 16 over L, or Fx equals F multiplied by 16 over the 2 times the square root of 89, and that's going to be simplified to F multiplied by 8 over the square root of 89. Using the same logic, if I know theta and Fy will use the sine of theta, or in other words, Fy equals F sine theta. What is sine theta? Sine theta is nothing but 10 over L, right? So Fy equals F multiplied by 10 over 2 square root of 89, and that's equals to F over, or F multiplied by 5 over square root of 89. Now I know Fx, I know Fy. We know that Fy equals 450, so 450 equals F times 5 over 89. Now I can solve for F. If I solve for F, it turns out to be 90 multiplied by the square root of 89. Now I know F, therefore Fx can be calculated, which is F times 16 over 2 square root of 89, and that's going to be 720. And from before we know that Fx equals Bx, so Bx equals 720 as well. We end up solving for all the forces needed to start drawing the shear force and bending moment diagrams. So let's go ahead. This is my beam. I'm going to start drawing. I'm going to start with the shear force. So we go down 250 kilonewtons, and now for the next point I know that the 7 kilonewton per meter is pushing me downwards, basically 7 kilonewtons per meter. So I'm at 250. I'm going to be pushed down for 4 meters times 7, so, and added to this previous value, I get 278. Now at this point, at point E, or the point where the pin is, I have two forces, 450 upward and 50 downwards. So if you think about it, the total force will be 400 upwards. So now I'm going to be pushed up 400 kilonewtons, reaching 122. And if I want to continue, I'm going to use the same logic. The 7 kilonewton is pushing me down 7 kilonewtons per meter, and I'm going to be pushed for a total of 16 meters. So 16 meters times 7, and I'm going to subtract it from the 122 to get to this value. Now my checkpoint is here, that this value better be 10 kilonewtons, and it sure is. Why 10? Because it should equal to the reaction at point B, so the shear force diagram closes. Alright, now let's go ahead and do the moment diagram. The moment diagram is much more fun. The moment diagram will depend on the areas under the curve. So I know the moment diagram is going to go downwards like this, causing a negative moment, and the value of the moment here equals to this area, and this area is negative, so the moment is going to be negative. Now how to calculate this area is trapezoidal area. So it's negative 250 plus negative 278 over 2 multiplied by 4, which is the length of the segment. I'm taking the average of the length multiplied by the total length of the segment. I get negative 1056. So it's negative 1056. Alright, this value should be negative, guys. Alright, I know that at the end of the beam, the moment is 0. So if this value is negative 1056, this area should give me positive 1056. Because if I add it to the negative 1056, I should get a 0. So if I calculate the area just to check, it turns out to be 1056. We draw it, and we're done. This is the shear and moment diagram for this beam. I will use a software to check my answers. Now let's use multi-frame to check the answer. Okay, first we go to the frame window. We start by creating our beam. Our beam is at 20 meters long, but it stops at 4 here, like so. We start from here until like here, which is 4, and then we draw another one from 4 to 20. Okay, now we go up 10, so let's go ahead and draw a member and then delete it. 1, 2, 3, 4, 5, 6, 7, 10, and the next member, or the tension cable, or the cable is going to go like this. Then now we can go ahead and select this member and delete it. this problem to work, first I need to define the sections. So what I will do, select a section. We have a custom section here which has virtually no weight, so I selected that, and I need to define the hinge, and here I need to define it as a fixed because it's a cable. But in the meantime, I will tell the program that it's pinned end, so there is no moment. It's just gonna act like a table. Now I'm done defining the frame. Let's go to this window and fix and zoom out. Now I'm gonna define the distributed load first. It's 7 pointing downwards, and I have some point loads here, which is 250, and I have a point load here which is 50. And before I continue, let me just show the load values 57 and 250. Now I'm ready to run the analysis. So we go to case, analyzes the statics, and boom, it's done. So this is the shear force diagram, and this is the moment diagram. Okay, so that's it, and I'll see you guys in future tutorials.